In this video, I'm going to do the simulation exposed in this document about a PSpice exercise, which is a power supply with a full wave rectifier. The full wave rectifier has 4 stages, which are the transformer. We have to talk how to define the parameters of the transformer to correctly adapt the 230 volts to 12 volts that we want in our power source. And then we're going to add a bridge, so the wave is going to be rectified. Another stage is the capacitor, and depending on its value, we're going to obtain different ripple waves. So the filter is an important part of the circuit. And finally, we're going to introduce the substitute of a Zener diode, which is in integrated circuits. We have a lot of regulators, so we're going to add a 7812 regulator to obtain the 12 final volts. Talking about transformation, it's important to say that we're not going to modify the coupling factor as I have seen in many exercises on the internet, just because the coupling factor of 1 is almost, which is the ideal transformer, is almost the same that a typical commercial transformer. In any case, it's not the parameter that we have to adapt to obtain the final voltage. So studying these relations we have here, we see that the transformation is basically done with the inductance values. So here we have the coefficient to transform the 230 to 12 volts. And here, supposing we have in the primary 1 Henry of inductance, is calculate the second value in the secondary. So these are the parameters we're going to give to make work our transformer. Next, we're going to add the bridge, which through the simulation we can see how the big input entrance is going to be modified here. When we delete this sign, we're going to obtain a better resolution. So here we can see the output of the transformer and then the rectified sign. And these are the RMS values. Then the filter is very important, so we're going to do a parametric sweep. We're going to define a variable for C1, and we're going to simulate and introduce 3 values for the capacity, and we're going to see how a lower capacity makes a bigger ripple and a lower DC signal. So how the higher the capacity, the higher the DC tension with a lower ripple. Finally, we're going to add the substitute of the Zener diode in a simple regulator, but now we always use integrated circuits like the LM78 12 volts, for example, to obtain the 12 in the output, or 0.5 to obtain 5 volts, etc. We're going to open the exercise. We're not going to do all the adding parts, which is very simple and easy to find on the internet as a basic manual. So we're going to quickly open the exercise, open the different parts we have seen in the document, and we're going to simulate them. Okay, this is the first one. As you can see, we have several schematics. And the first one is the explanation we said about the transformer. So in the second schematic, in this one, we're going to adjust these values only. We have here, and we have defined the transient analysis. We can see it. It's only about 60 milliseconds, which is 3 cycles, since we have an input signal source of 50 Hz. The amplitude of the signal is 325, which means that the RMS value is 230. So the transformer, as we can see here, has the values we talk about in the document. Capacity, and the other coupling factor is 1, is not the adjusting that we say. And we have test makers only to see the different waves in the input, then the near to 12 volts output of the transformer, which must be around 14-16 volts. Not the RMS, but the peak values. We're talking about peak values now. And then we have the bridge. We have to say only about this that all the parts of all these circuits are found through the libraries we can add here. So we find in PSpice all the libraries we want. Okay. And the most significant for us are analog, where we found the transformer, for example, which is this, okay. Or another one is the diode full bridge, the other library. So now we're going to simulate this circuit, and for that we put 2 voltage markers here in the input and output of the transformer, and a differential marker because here the ground is adjusting only in this part of the circuit. So here we have to put that differential marker to know how the signal is in the output. Okay, so now we're going to simulate it, running it. And here we can see the input, which is a maximum of 200, 325. We can see approximately the values are correct. And here in green we have the rectified signal, and this is in the red we have the output of the transformer. Okay. If we want to see it better, the scale in the output only, not the input, we can delete this signal so we can see the output of the transformer and the rectified signal we have here. So with the capacitor we're going to add next, we're going to try to convert the curve where we're going to see the ripple and the corrections where it has the filter stage. Here always we can see a little different, and that's because of the diodes. Each one is about 0.7 volts of difference, so the sign goes through 2 of them, and that's why the voltage drops a little, but not significantly. To simulate the full-wave rectifier adding the filter, which is a capacitor with different values, we're going to do it thanks to the parameter we define here. Only to say that the parameter can be added with the special library If we find here param, you can see that we can add it here. So then we have to add the C1 bar parameter through this new property. We could add it here. We already have it here, but here is how you do it. Apply it. Okay, then it appears here. So with this value, which is going to be the parameter, and through the simulation we can give a list value of capacitors here in the parametric sweep. We're going to jump the first 40 milliseconds, which is 2 cycles of the 50 Hz signal, only to show the charge of the signal is almost, you can see better the ripple. And here, as I said, you have the different values of the capacitor, which is 1000, 2200, and 4700, as I said before in the document. So running this, we can see the different values of the capacitors, and here we can appreciate that the less value of the capacitor, you have doubts with which capacitor is. You have here the trace information, so this is 1 millifarads, which is the 1000 microfarads. Okay, this is the less value of the capacitor, which has more ripple, and as a medium it has less DC output. Conform the ripple is less and the capacitor is higher, you have a better DC signal, higher and more flat. So the best value is this, okay, with the 4700 microfarads. Finally, we can add the regulator, which is only this is only a lead. We are only adding here a diode with a resistance to protect it. This is a LED to say it's okay on the output of the bridge, and then this is a typical configuration we can find in any data sheet of this circuit. Okay, so here the sign is what we showed after the ripple. Here we have the 2200 microfarads, so it's about 16 volts or whatever with a ripple sign, but here after the output is going to be flat and 12 because the regulator has that value. So with this regulator we put marks before in the filter output and after the flat the output of the regulator, so we compare and see that it's working perfectly. We have already selected the transient analysis for the schematic 3, which is this. Schematic 3 is okay. So if we run it, we'll see the outputs and the difference between both. Which is working. Then you see this is the signal that we have seen only in two cycles, but this is for 10 seconds of time, and this is the output, so it's working perfectly, 12 and flat. And of course you can put or modify a little if you want a variable voltage regulator. You can substitute it for another one like here, which is LM 217, and this is the formula for the output. So if you modify this potentiometer, you're going to adjust the output. That's all.